Good morning, everyone. My name is Andrea Iadarola. I'm attending the second year of my PhD program in the Department of Mechanical and Aerospace Engineering at Politecnico di Torino. I work in the field of biocomposite materials in the work group of Professor Davide Paolino. This study, named Quasi-static and dynamic response of cardanol bio-based epoxy resins, effect of different biocontents, comes from a collaboration between the Department of Chemistry of Università degli Studi di Torino and the Material Sustainability Engineering Department of Centro Ricerche Fiat from the Stellantis Group. In recent years, environmental and economic concern is growing due to limited petrochemical resources, leading to growing interest in renewable resources, especially in the automotive sector. Indeed, in the automotive industry, it's not only a matter of greater sustainability and cost efficiency, but also a demand for European regulations. In fact, the European Community regulations are promoting the use of sustainable and green materials to lower the overall carbon footprint in cars. The majority of structural composite material use petrol-based epoxy matrices, which are not easily recyclable, and therefore they represent a negative impact for the environment. For this reason, petroleum-based materials have to be substituted by polymers derived by sustainable resources. The most promising and ready-to-use technique to lower the carbon footprint in composite material production is the use of bio-based resins, since their application does not affect the manufacturing process. In our study, we wanted to investigate the chemical and mechanical properties of two commercially available bio-based epoxy resins characterized by two different biocontent, in order to obtain 4 different resin mixtures by mixing them together. In particular, we wanted to mix an epoxy novolac resin with a very high biocontent with cardanol-based epoxy resins with different weight percentages, as you can see from the table. And we obtained 4 different total biocontent, which were computed by means of the rule of mixtures. The methodology consisted on a degassing phase before curing in order to avoid the presence of void into the resin mixtures, followed by a 3-stage curing process, and after that the surfaces of the spacemen were polished in order to flatten the surfaces. Chemical and mechanical properties of the resins have been investigated at increasing biocontents by means of quasi-static and dynamic tensile tests, by means of a digital image correlation system in order to acquire the strain data. Moreover, a differential scanning calorimetry analysis was performed on already cured specimen in order to verify the complete cross-linking of the resins. And finally, the fracture surfaces were analyzed by means of a digital microscope. The materials adopted were, as I said, 2 different bio-based resin characterized by 2 different biocontents. Both of them were from the same supplier, which is Ciardiello, and one is a cardanol-based epoxy resins, and the other one is an epoxy novolac resins. Then the differential scanning calorimetry tests were performed by Università di Studi Torino using a TA instrument working in controlled atmosphere of nitrogen, performing a curing ramp of 20 degrees Celsius per minute until 200 degrees Celsius, starting from minus 40 degrees Celsius. From the laboratories of Centro Ricerche Fiat, we performed the tensile test by means of an MTS tensile testing machine provided with a 25 kilonewton load cell and with a digital image correlation system from LaVision. In this slide, I reported the results coming from the differential scanning calorimetry test, and we can see that there is no exothermic peak because there is no cross-linking reaction, since the tests have been performed on already cured specimens. But from the result, we can see a reduction of the transition glass temperature values by increasing the total beer content. Here are reported the stress-strain curves coming from the tensile test for the 4 different resin blends, considering the 3 different strain rate values and with the objective to highlight the effect of the total beer content. In fact, by increasing the total beer content, we can see reduced strength and modulus, whereas by increasing the strain rate, the strength and modulus are higher. Generally, we can see higher elongation for a total beer content higher than 50%, but overall, we can see a reduction of the softening behavior by increasing both beer content and strain rate. Here I reported the same stress-strain curves for the 4 different tested materials, but with the aim to highlight the effect of the strain rates. In fact, by increasing the strain rate, we can see that we obtained a higher modulus and a reduced maximum elongation. Whereas by increasing the total beer content, we had a reduced strength and a reduced elastic modulus. Overall, we can see a repeatable trend considering different strain rate at different beer content. In this slide, I reported the values coming from the tensile test for the elastic modulus, considering the 4 different tested materials and 3 different strain rate. As you can see, by increasing the beer content, we have a linear decreasing trend, and this decreasing slope is almost the same for the 3 different strain rates. By increasing the strain rate, we have an increase in the elastic modulus. Whereas here I reported the values for the ultimate tensile strength, considering also in this case 4 different material and the 3 different strain rates. And also in this case we have an almost linear decreasing trend by increasing the total beer content and an increase of maximum strength by increasing the strain rate. Finally, here are represented some fracture surfaces coming from a representative specimen after failure. And as we can see, by increasing the total beer content, so going from the top to the bottom, we can observe slightly more ductile fracture surfaces. Whereas by increasing the strain rate, so going from left to right, we can observe slightly more brittle fracture surfaces. Overall, we can say that the failure happens due to the presence of a void. For example, in the specimen of 27 total biocontent, 27% total biocontent, tested in quasi-static conditions. And these can be also verified by means of the digital image correlation system. In fact, in the case of the specimen characterized by the 27% of total biocontent tested in quasi-static condition, we can see from the digital image correlation images that there is a concentration of the strain in a particular zone of the area of interest, which is also the zone where the failure happened. So, finally, the effect of the strain rate and the biocontent on the tensile properties of bio-based resin was analyzed in this study. And in conclusion, we can say that a reduction of the transition glass temperature values have been found by increasing the total biocontent. Moreover, a linear reduction of elastic modeling and strengths were found by increasing the biocontent of the base resin, whereas an increase of modeling and strengths was observed by increasing the strain rate. Most importantly, from the analysis of the resins with the lowest biocontent, it can be seen that they have comparable properties with epoxy resins commonly used for structural applications. Therefore, just replacing the epoxy resins with bio-based one, the environmental impact can be reduced. In future studies, we want to investigate the behavior at different temperature of the analyzed materials in order to evaluate the application in the automotive field. So thank you for your attention, and if you have any kind of question, this is my contact and I will be glad to answer.